My name is Benjamin, and I'll be presenting today about improving reasoning with multi-agent systems. The goal of today's project is to combine Reason LLM and RL techniques to fine-tune the Quantum 0.5 billion parameter-based model for math reasoning. It's important because most people don't have the compute for larger models. It's especially important for researchers to have new techniques to train smaller models before scaling to larger models. Math reasoning is an interesting problem because it's so challenging for LLMs, especially small models. The skill helps unlock several more advanced capabilities. The tasks are raised with the countdown dataset. Models can target number and need to use the other numbers exactly once in a mathematical expression that equals the target. The model outputs are correct, the equation gets the square of 1. Once an equation with the wrong numbers, when it doesn't use the target, it gets the square of 0. Otherwise, it gets the square of 0. Because it's hard to generate a correct response every time, we instead decided to generate k responses and pick the best one. Though picking a response is also hard, so we split it into extraction, evaluation, and selection, each with a separate lower adapter for training. The lower adapter is based on a base model that was fine-tuned on small talk for a structure following. By separating the tasks, each agent can improve independently, even if the other agents have poor quality. This is accomplished by having each of the agent's loss function be based on what the ground truth would be if its outputs were correct instead of what it should have been. This also helps debug where the system makes a mistake. For example, with the selector agent, you choose the incorrect example, but the critic agent said it was correct. That means the critic agent needs to improve, and the selector agent is not penalized for selecting it. Here's an example. The input is 186.97, and the target is 10. Generator, get this, and output 16 different chain of thought responses, each with the same answer to like this. The extractor agent extracts the answer from each one and invokes the calculator tool by adding an equal sign to each answer. The calculator tool computes the expression value and appends it to the response in this example. Because the extractor agent was often the worst performing agent, we also implemented automatic extraction that would programmatically extract the answer and compute the expression value. The critic evaluates if the expression value matches the target and if each number is used only once, and lets each answer with the expression value promoted through its model and outputs whichever correct or incorrect has higher budgets for the next token. We pre-ran the critic evaluations to the extracted answers for the selector agent to choose the final answer. The selector agent can also pick none of them if it thinks all of the responses are incorrect. We evaluated our system with both agent extraction and automatic extraction on 2 different base models and compared it against the base model results. With agent extraction, the system was similar or slightly worse than the base reasoning model. With automatic extraction, we saw substantial improvement, especially for the SFT model, which improved from the score of 0.32 to 0.62. We believe it's because the SFT base was inconsistent. 16 samples allows the multi-agent system to identify a good response. When we tried using a single response probe to extract, evaluate, and select, the performance was extremely poor, so splitting into subtasks was important, even without fine-tuning. Similarly, when we added examples of the problem, adding examples of the problem was critical for the agent to understand the difference, especially without fine-tuning. Some limitations in the extractor agent problem was very hard to do. We needed to repeat the instructions for invoking the calculator tool several times before the extractor agent figured it out. There are also several different points of failure. In particular, the extractor agent was usually the lowest performing agent, so the critic and selector got bad data. However, with these results, we did not fine-tune the agent models at all, and we expected this to provide a significant boost in performance. We also plan to add multiple groups of agents and add multi-agent debate, which will help add resiliency to prevent a single point of failure. Thank you for watching my presentation. I